Have you ever just stared into a mirror and wondered, what is actually going on in there? I mean, it kind of feels like magic, right? But it's all just pure physics. So today, let's pull back that curtain. We're going to decode the science behind your reflection, and we'll start with the most basic question of all.
All right, so first things first. Where is that person looking back at you? Like, really? Are they on the glass? Are they behind the glass? You know, this one question, it's the key to this entire puzzle we're about to solve together.
So, to figure out where your reflection is, we've got to understand what it is first. We're about to go on a little investigation, and our very first clue is figuring out what kind of image we're even looking at. You know, in the entire world of optics, with all the different mirrors and lenses you can think of, it turns out every single image you could possibly see, it's one of just two types. That's it, just two. Real or virtual. That's the whole shebang. If you can get your head around this one difference, it's like having the master key that unlocks everything else about mirrors. So, what is the difference?
Okay, here it is. A real image is formed where light rays actually come together. Think about a movie projector hitting a screen. Light is physically landing there to create that image. A virtual image, on the other hand, is formed where light only appears to be coming from. Your reflection in a regular flat mirror? Perfect example. It looks like it's behind the glass, but come on, we know there aren't any actual light rays back there. It's basically a super convincing optical illusion, kind of like a mirage.
Now, if we want to talk about these images like a physicist, we need a language for it. And that language is built on just 4 simple variables that can describe any reflection perfectly. First up, we've got P. That stands for object distance. It's just how far you, or whatever the object is, are standing from the mirror. Easy enough, right?
Next is Q for image distance. This is how far your reflection seems to be from the surface of the mirror. Now, your gut might tell you it's the same as P, but is it really? We're about to find out.
Then you've got H for object height. Pretty simple. That's just your actual height. Or, the height of the coffee cup you're looking at in the mirror. And last but not least, H prime. That's the apparent height of the image in the mirror. Is it bigger, smaller, or exactly the same size as the real deal? So these 4 things, P, Q, H, and H prime, that's our entire toolkit.
Okay, let's put it all together. This diagram right here is our map. You can see the actual object over on the left, with its distance P and its height H. And then, on the right, there's the virtual image, with its apparent distance Q and its height H prime. This one picture visualizes the whole language we just learned. All right, now for the really cool part. Physics uses this simple little code, just positive and negative signs, to tell us everything we need to know about an image. This isn't just random math. It's like a secret language that describes what's really happening. And here is the biggest secret of them all. In optics, a negative sign always means the image is virtual. A positive sign always means it's real. Just by knowing the sign of a number, you instantly know the most fundamental thing about the image. This one little rule is crazy powerful.
So let's use this code. Check out this table. For a simple flat mirror, the object, that's you, is always out in front, in the real world. So your object distance P is positive, but your image appears to be behind the mirror, where light isn't actually going. That means the image distance Q is negative. And what does that negative sign tell us? That the image is virtual. See? We just proved it mathematically.
Okay, so we know where the image is, and we know what kind of image it is. But what about its size? And is it right side up? For that, we need one final piece of the puzzle.
It's called lateral magnification, and we just use the letter M. All it is a simple ratio that compares the image's height to the object's height. And this one number is amazing because it tells us 2 things at once, the image's size and whether it's been flipped over.
And here's the formula that just ties it all together so neatly. Magnification M is the image height H prime divided by the object height H. But here's the really powerful part. It also equals the negative of the image distance Q divided by the object distance P. This one equation is the bridge between height and distance.
So, we get what the value of M means for size, right? If M is 2, the image is twice as big. If it's 0.5, it's half the size. But what about the sign? What does a positive or negative M actually tell us? Well, it's actually super simple and kind of beautiful. A positive magnification means the image is upright, standing the same way as the object. A negative magnification means the image is inverted. Yep, it's been flipped completely upside down.
So now you can break down any image from any mirror in just 2 simple steps. Step 1, check the sign of M. Is it positive, meaning upright, or negative, meaning inverted? Step 2, look at the actual number. Is it bigger than 1, so it's magnified? Smaller than 1, so it's shrunken? Or is it exactly 1, meaning it's the same size?
And there you have it. You've got the complete toolkit to decode any reflection. So the next time you see yourself in the curved surface of a spoon, you'll know exactly what's happening. Is the image real or virtual? Inverted or upright? Magnified or minified? You know the code now. Which, of course, begs the question, why does the front of the spoon flip you upside down, but the back doesn't?